Set theory or theory of sets is the core concept in measure theory and probability. So, this lecture is aimed to give an idea of some basic notions of set theory. This lecture will give some brief introduction to some of the basic concepts which will be required in subsequent lectures. We will revisit some of the known concepts, known results, and the results related to set theory will be discussed with the help of examples. We will try to define different sets, for example null sets, universal sets, and different set operations and their properties in details. We will try to give as many examples as possible in each of the cases. This lecture will give the basis of subsequent lectures, and this will give us an idea how we should progress. To start with, first we have to define what do we mean by set. We have so many definitions available. So, basically a set is an unordered collection of objects referred to as elements. So, a set consists of few elements. Every member of a set is called its element. A set is said to contain its elements. I will give you few examples. For example, the set 1, 2, 3 is a set containing 3 numbers 1, 2 and 3. Set is usually represented by braces. Consider another example. Here it is a set consists of elements 1, 1, 2, 3, 3. Look here, 1 is repeated twice, so is 3. But this is nothing but a simple set 1, 2, 3, since repetition is irrelevant in case of a set. Now, this set 1, 2, 3 can be written as 3, 2, 1 because sets are unordered. So, ordering does not have any effect on a set. Now, this is another set, it is 1, 2, 3 up to 99. We can say that it is a set of positive integers less than 100. Or we can have some infinite set too, where the number of elements is not finite. If you consider this set 1, 2, 3, 4 and so on, and it is a way to denote an infinite set. In this case, this is a set of natural numbers. It is not necessary that all the time a set must have an element. If we have a set which does not have any element, we call this as null set or empty set, and this is denoted by usually phi. If phi is a null set, then we will have another set called universal set, that is omega. This is set of all elements currently under consideration. So, this is omega is called the universal set. Now, I will discuss few of the important sets that we often use. The first one is the set of natural numbers, non-negative integers. We denote it as script n. So, it is a collection of 0, 1, 2, 3 and so on. Then we have a set of integers which contains both positive and negative integers as well as 0. And if we want a set of positive integers, we can just write 1, 2, 3 and so on. Then we can have a set of rational numbers denoted by script q. This is a collection of all p by q form, where p and q both belongs to the integer and q is not equals to 0. This is the set of rational numbers. And scriptor is the general notation we use to denote the set of real numbers. Once we have an idea about set, next we want to get an idea about the subset. We say x belongs to S, that means x is an element of a set S. So, x belongs to S means x is an element of S. If x does not belong to S, that means x is not an element of the set S. Now, we say A is a subset of B. This is notationally written in this way. This means that A is a subset of B. We can interpret it in this way. That means B contains A. B is a bigger set. Or we can say every element of A is also in B. Every element of A is also in B. Or we can say that for all x, if x belongs to A implies x belongs to B, then we can say that A is a subset of B. Now, if I remove the equality, it is called a proper subset. A, this symbol means A is a proper subset of B. So, whenever we have two sets, one is a subset or one is a proper subset, the next thing is that when we should say that two sets are equal, that is the equality of sets. So, we say A is equals to B if and only if A and B have exactly the same elements, then only then we can say A and B are equal. So, we can say alternatively that if and only if A is a subset of B as well as B is a subset of A. If both the condition holds, then we can say that these two sets are equal. Or we can define in other way too. We say for all x, if x belongs to A implies and implied by x belongs to B, then we say that these two sets are equal. So, if we are asked to show the equality of two sets A and B, what we have to show? We have to show that A is a subset of B as well as B is a subset of A. Once these two conditions are simultaneously satisfied, we say two sets are equal. Now, we will consider a few examples. Consider the two sets. The first set consists of 1, 2, 3, only 3 elements, and the second set consists of 1, 2, 3, 4 and 5. So, if the question is asked that whether the first set is a subset of second set, the answer is yes, because every element in 1, 2, 3 belongs to the set contains 1, 2, 3, 4, 5. And if you see that it is a proper subset, because in the second set 1, 2, 3, 4, 5 they have two elements which are extra 4 and 5 which do not belong to the set 1. So, the left hand set is a subset, proper subset of the right hand set. Now, if I ask you the question that is phi the null set is a subset of 1, 2, 3? Remember that phi is a null set, empty set, it does not contain any element. So, is the null set is a subset of any set? The answer is yes. Now, whether this phi, this null set belongs to a particular set 1, 2, 3? Yes, the answer is no, because phi is not a member in this set. If this question is asked that whether phi is a subset of a set which contains phi 1, 2 and 3, the answer is yes, because phi is a member there, and moreover the right hand side, the set on the right hand side consists of more elements, and the condition is satisfied. So, it is yes. Is phi in this set which consists of phi 1, 2 and 3? The answer is yes. Now, one tricky question, that are phi and the set consists of phi the same? The answer is no, because in case of phi we do not have any element, but in the second case it is a set where we have an element which is phi itself. So, they are not the same. Once we define the set, now what sort of algebraic operation we can do on these sets? The first operation that we will be doing is called union. So, we say A union B, this is once again will result in a set which contains all elements of A and all the elements of B. For example, if you take two sets 1, 2 and 3 and take the union of this set with another set 3, 4, 5. So, the resultant set will be 1, 2, 3, 4, 5. even if 3 is repeated twice, but as we know that repetition doesn't have any meaning in set, so it will be 1, 2, 3, 4, 5. Similarly, we can define intersection. A intersection B is the set which contains all the elements which are in both A and B. For example, if the set we have is 1, 2, 3 and 3, 4, 5, just like the previous one, if I take the intersection, the common or the element which is in the both A and B is 3. So, we will have a singleton set with element 3. So, this is the intersection of A and B. We can define the difference between two sets A minus B as the set which contains all the elements which occur in A but not in B. So, we are talking about elements which belongs to A but not in B. For example, we have two sets, the same sets that we have been taken so far, 1, 2, 3 and 3, 4, 5. If I take the difference, then I will get a set consists of two elements 1 and 2. Once we have a set, we can define a complement of a set. We write A complement as a complement of a set A, which contains everything which is not an element of A. Now, this complement makes sense whenever we are talking about any universal set, because unless you define your universal set, we do not know what is beyond A. So, whenever we are saying which is not an element of A, that we must be talking about the elements which does not belong to A, but belongs to the universal set. And the number of elements in a set is called cardinality. We define cardinality as mod. And for this set 2, 4, 6, 7, we have 4 elements. So, cardinality of this set will be 4. Next, we will try to focus on the properties of set operations. There are so many properties of the set operations. I will be discussing a few. The first property that I will be discussing is called identity. So, phi is your null set and omega is your universal set. So, it can be seen that A union phi. So, whenever I am taking the union of a set with a null set, it remains the same. That means A union phi is M, A, and A intersection omega, whenever I am taking the intersection with the universal set, I will be getting A. So, this is called the identity. Then we have a condition of idempotent. So, that means if you take the union of the set, same set, then you will be getting the same set, whereas if you take the intersection of same sets, you will be getting the same set. We call this as idempotent. Then we can show that the set operations are commutative. That means if for two sets A and B, A union B is same as B union A, or A intersection B is same as B intersection A. So, this is the property we call as commutative. Then we can have associative property too. It means suppose we have three sets A, B and C. Now, we are taking the union of first two A union B, and we are taking the union of C with the union of the first two. This is same as taking the union of the last two B union C and then take union with A. So, this property is called associative. The same property can be observed when we are doing intersection. So, if I take the intersection of the first two set and then take the intersection of the third, it is same as taking the intersection of the second and third together and then take the intersection with the first one. This is called associative property. Then we have the distributed property also. So, distributed property, it says that once again I have a set of three sets A, B and C. So, A union B intersection C is same as A union B intersection A union C, whereas if I interchange the union and intersection, then A intersection B union C is same as A intersection B union A intersection C. This is the property we call distributive. So, we can have so many examples on these properties to show these properties. The next property and next important law that will be used in subsequent lectures is called De Morgan's law. It says that if you have two sets A and B, then A intersection B complement is same as A complement union B complement, and A union B whole complement is A complement intersection B complement. The essential message is that if you take whole complement of union or intersection, union will be replaced by intersection and intersection will be replaced by union, whereas the individual sets will be replaced by its complements. Though I have taken only two sets A and B, this can be extended to any number of sets. It is a very powerful law that will help us in subsequent lectures. So far, we have discussed the properties of different set operations along with different types of sets. This will create the base on which we will go further. So, in my next lectures, I will be discussing sequence of sets, their limits and so on. So, this is very basic and core, and to learn measure theory and probability, one has to learn the set theory really well.